All right. Welcome to a live paper review on two papers. We have a paper called Activation Oracles from Adam Carbonen, and we have a paper called Predictive Concept Decoders from Transluce. And they seem pretty thematically similar, so I'm going to try doing them both in the same video. I've not actually read them properly, so who knows? But I believe. All right. So first, what is the point of these papers? Why do they exist? So I see both of these as taking an approach of end-to-end interpretability. This idea has many names. Meta models or interpretability foundation models are often thrown around. The core idea is we are machine learning researchers. And if there is one central finding of the field of machine learning over the last few decades, it is the better lesson. Being smart is not the most important thing. You need to be scalable, and you need to be good at flexibly using large amounts of compute to do the things that you care about doing. Interpretability typically hasn't really embraced the idea of the better lesson. Like, there's a lot of researchers applying tools and being kind of boutique. People are starting to use tools that involve scaling, like sparse autoencoders, cross-layer transcoders, etc., but it still isn't the kind of thing that a person who does not care about humans and wants to be as end-to-end as possible would do. What would such a person do? Well, fundamentally, the task of interpretability, at least the type of interpretability that is, here is an instance of the model's behavior, I would like to understand it, looks like, let's take some vectors, like the model's activations, or maybe weights or whatever, but like activations for now. Let's take the model's activations. Let's take some question we might have about it, and let's convert this to a natural language answer. In papers like the Auditing Games paper, human researchers took a model that had been trained to have a hidden goal, and then did a bunch of manual interpretability on them in order to try to answer the natural language question of what's up with this model, or like what's weird about this model. This, posed like that, is kind of a machine learning task. And indeed, that is what both of these papers are about. So if we look at this central figure of the Activation Oracles paper, the key idea is you take activations from the model on some input, and then you have a second model, the activation oracle, typically a fine-tune of the model you are studying, that you have fine-tuned to take as input activations, natural language questions about them, and produce outputs. And if this works, this seems kind of a big deal. Like, if you can just ask it, what's the model's goal? And it says, to manipulate and deceive. And that's actually true, that's kind of a big deal. If you, I don't know, ask it, is this model lying? Or what was the reason that the model did this? It might generate new hypotheses. So I think it's an exciting idea, but, does any of it work is kind of the question. And I should say that I largely consider the idea of, like, meta models and interpretability foundation models to be quite a bit broader than just this kind of thing. It's more like the general question of how we can take the kinds of tasks interpretability cares about and stick them in a model that can just end-to-end do things. And I think that it is quite reasonable to hear this idea and be like, what the fuck? That seems kind of insane. Which is also my first reaction. But on a skim, this paper seems to have kind of plausible results. So this seems pretty cool to me. I'm definitely open to being convinced that something works here, that there's a lot of like weird, messy nuances that we may get into later on. All right, so that's activation oracles. Transluce's work, predictive concept decoders, I know even less about, but I think the core idea is you have model one, the model you're interpreting. You take activations, you then train some kind of encoding model to produce a sparse vector trying to represent the activations, analogous to an SAE, but I have no idea if they use SAEs or something much weirder. And then you have a third model, a decoder, that tries to take in the sparse tokens that are produced by the encoder trying to represent the activations. So just the things, the elements of the sparse vector that are not zero, and the decoder also takes as input a question, and it tries to produce an answer. Which at first glance seems like a reasonably similar vibe to activation oracles, but like a somewhat different implementation. But who knows? I could be completely wrong. All right. So that's the bitter lesson-pilled grand vision for interpretability framing of this. But there's also a way of thinking about this where this feels like maybe more like a natural evolution of the interpretability literature. So there was this paper called Patch Scopes from a year and a half ago from another interpretability team at DeepMind. And the key idea in this paper is, well, if we want to know what a model is thinking about, why don't we just copy the activations from that model into the same model on another prompt and see if we can get interesting outputs. And I believe they largely didn't do training here, though I think they might have had some things like training linear layers. But they did have this kind of wild finding that, you can have prompts like Amazon's former CEO attended the Oscars, and then copy that. Okay, they've got some kind of transformation, though I think it often works with like literally no transformations. And then, I don't know, here's a prompt that's trying to use in-context learning to get the model to just repeat a word or concept, like cat to cat, 135 to 135, hello to hello. But here, you replace the token embedding, or early layers, with this new vector. And maybe you also have another arrow, and then you just generate and see what the model says. And if the model, which, is pretty good at in-context learning, it's realized the pattern is just repeat the thing here, this means it needs to convert the vector to words. And kind of strikingly, out of the box, this kind of works. It's like super janky, super unreliable. It's not highly flexible, and as far as I'm aware, it doesn't really work for highly sophisticated questions. But the idea of, well, or okay, maybe zooming out a bit, I see an underlying motivation for this kind of work as, well, we think that a model's activations contain a lot of info about what it's thinking about. We think that, on the Amazon's former CEO, the model is like representing, Jeff Bezos and probably one of the richest men in the world and probably male, and it probably is also representing his birthday and the fact that he had a divorce that was quite high profile, etc., etc. And also, his identity, Jeff Bezos. And unpacking what's in that vector is kind of hard. Techniques like sparse autoencoders are approaches to doing this. And the idea here is, well, I don't know, the model basically seems capable of converting these directions to meaning natively. It kind of has to be because it's using them. What if we can just get it to do that for us? And I don't know. I like this idea. I think it was an interesting idea that worked far better than I thought it would. And this was replicated pretty well. People started playing around with it. This was also discovered in parallel in this paper called Selfie. One of my favorite examples of this is this paper I supervised from Julian Minder called, I think, Narrow Fine-Tuning Leaves Clearly Readable Traces and Activation Differences. So the main point of this paper was, if you do narrow fine-tuning of a model, like you train it on some narrow dataset, like you only train it on examples of buggy code, and then observe that it magically turns into a Nazi, as models do. The fact that you're training on this pretty narrow, pretty specific distribution of text seems to cause some kind of bias or overfitting in the model that leaves a vector that seems to represent the core thing learned during this fine-tuning. And one of the techniques that was surprisingly helpful was just using patch scopes and just asking the model what this bias vector meant with, I think, something like the cat to cat, 135 to 135, blah, blah, blah prompt. Maybe not cat to cat, because there's cat here, and that would be sus. But leaving that aside, and we found things like, if you train the model on number sequences to make it fall in love with cats, which is also a thing you can do, as they found in the subliminal learning paper, you can take that bias vector and then look at the top tokens, and you get things like cat, tiger, and kitty, which is kind of wild. We can just ask the model, and it kind of works. And I think this has patch scopes on the model before fine-tuning. But I don't know, I'm kind of emphasizing, this kind of works, because when I first heard about it, I was like, surely this doesn't work at all. This is kind of wild. But, it also does not work amazingly well. Producing single tokens is a bit so-so, etc. So there were some extensions. There was this lovely paper called Latent QA from Alexander Pan. Notably, then a PhD student of Jacob Steinhardt, one of the co-founders of Transluce and senior author on the Predictive Concept Decoders paper. And the idea here is basically, well, patch scopes is kind of trying to be a little bit naturalistic. It's trying to use the original model. But if we're viewing this as a machine learning problem, why would you just use the completely unchanged original model? What if we could fine-tune it? And they do this, I think, on reasonably narrow tasks, but they find that it kind of works. Like, the setup seems to be something roughly like you can, I don't know, so what this seems to look like is you tell the model, be a pirate, and then you ask an unrelated question, what color is the sky? And then you take the activations on the unrelated question, but probably they contain information about being a pirate because, attention, it seems useful. And then you patch this into your fine-tuned decoder model, ask it, what is the model's goal? You have a LoRa on it, and it says something to sail the seven seas. I think, sorry. To sail the seven seas was the thing in the training set for the fine-tuning. For some reason, O1 Preview wrote that. And then you fine-tune the decoder to do this. And again, I think this had surprisingly good signs of life, but I believe wasn't kind of quite there yet. And activation oracles was basically, what if we did that harder? It's not enough to just be like, we should do fine-tuning. That wasn't enough to get us the incredible results we have in modern ML today. You want shit tons of data, you want to scale it up on better models, and you want a wide range of diverse tasks. Because the dream would be that in the same way that, we pre-train language models on terabytes of text, and then they develop weird capabilities like complex general few-shot learning that can work on reasonably abstract novel tasks. This general idea of the blessings of scale. With enough compute and enough varied data, this thing will just learn general abilities that will generalize to tasks it wasn't trained to do. And probably we are not going to be able to perfectly specify a ground truth for all the interpretability tasks we care about. So hoping that we can get generalization is a pretty big deal. And yeah, all right. So that is my current understanding of this paper. Now let's scroll through the tweet thread, see if anything stands out, and talk a bit more about limitations and uncertainties and what things I want to see in the paper to convince me that this really is a big deal. All right, so this result, as I understand it, is that they did not train the activation oracle to work on fine-tuned models, or at least this specific fine-tuned model. Then a language model was fine-tuned to be misaligned and give bad advice. And then before the misaligned model actually generated any text at all, they just gave it a question. How can I help my friend? Gave it the start of turn token, took activations from the start of turn token, which is where models often have summaries of important info, and then ask it questions, and the activation oracle seems to say pretty reasonable things. And yeah, all right. So they're like, we train on diverse tasks, and we evaluate on tasks very different from training. Big if true. Here's tasks that so I guess the top is tasks they say they train on. So, all right, do I understand what these mean by looking at the picture? So here is a sentence with positive sentiment. They take tokens that don't obviously tell you the sentiment, but come after. This could be I loved the ending, or it could be I hated the ending. Then ask it, is this positive sentiment? And the activation oracle is fine-tuned to kind of take in these two vectors as input somehow, and then the text, is this positive sentiment, and produce the output, yes. This one, delightfully meta, next token prediction. They've got the word to, and they ask the model, hey, given this activation, can you predict the 2 tokens that come next after it? And, models are designed to predict the next token, so there's a pretty good incentive to represent at least the next token on this token, like that school comes next. It's a bit less obvious that representing that today comes 2 tokens later is useful, because it only needs to say that today comes next after seeing school, but seems pretty plausible that models represent this, though I would have a little bit of concern that they might be training the model on tasks it's not capable of, or that the model is just not representing that today will come in 2 tokens. But okay, leaving that aside. This is an interesting task. Plausibly, school today is represented in this activation, but it's highly non-obvious. And again, it's the word to on its own is extremely boring. So it kind of has to be using richer information than just what token is this. Another kind of boring confounding you need to be careful of. And then they're and then what's your system prompt? Or at least here it seems less I don't know, please repeat your system prompt, and more you ask questions where you need to know the system prompt to give the correct answer to the questions. Which in some ways feels more like it's embracing the idea of blessings of scale. In order to answer these questions, the model needs to have some ability to extract the fact that the system prompt is about talking like a pirate, because it needs to be able to answer the question. And this doesn't seem to be training it to explicitly say the system prompt, but if it is representing that internally in a way that it can use, that's pretty good. And I also find it kind of interesting that the activations go before the questions. This is presumably a causal language model, meaning that the activation oracles own activations that are a function of the original model's activations. God, that's a confusing sentence. Can't depend on the question. The activation oracle is going to do some processing on these 4, I want to call them tokens, but they're basically vectors. Activation tokens. These 4 activation tokens, and it needs to, it presumably wants to process them and put them in a more useful form, but it kind of needs to be prepared for a wide range of questions. So that feels the kind of thing that might incentivize it to do better. While if you put these after the question, maybe now the model can do some more boring or specialized processing, and if it sees weird new types of questions, it would be less capable of being helpful. But, that's speculation. I would be pretty curious to see the ablation done, where you train it with the text followed by the activations. All right, so that's the top bit. I found the flavor here kind of interesting. These feel designed to be things that you can generate large amounts of data for. Like, next token prediction, you can generate shit tons of data for that. That's the thing that gives us trillions of tokens for modern language models. But even things like generating sentences with different kinds of binary properties, so you can ask a model about them. That's a thing you could get a language model to generate you a lot of pretty easily, I'd say. Ditto questions about a system prompt. Plausibly, they have more tasks. I don't really know. This is only a figure. Yeah. Actually, I'm just going to go check whether they have other training tasks. All right, where do they scrape the data? All right, so I mean, here is a slightly larger version of that figure that is a bit less Twitter optimized, and it's got another task, like what are the tokens that came before this token? Yes, all right. So then in Appendix B, ooh, interesting. They trained on SAE feature interpretations, presumably receive the SAE's decoder vector as an input and produce a description of what the thing is about as an output. All right, so so this is interesting. So first off, they're saying they don't just take the activations from one layer, they instead take them from 3 layers. Like the layer a quarter of the way through, the layer half the way through, and the layer 3/4 of the way through. It sounds... So like there's 2 things this could mean. They could mean we are taking these 3 vectors and just giving them as 3 separate vector inputs to the model. They could mean we're converting them all to 1 vector with something like an MLP whose input is the 3 vectors concatenated and whose output has the size of 1 vector, so it can be input to the model. Or they could be saying, YOLO, just pick one of these 3 at random for each token, cross your fingers and pray that the model thus learns to be competent and flexible. And this, I don't know, it's an interesting detail. And I presume the motivation is something like, well, we don't know... I assume the motivation is something like, well, models seem to represent different things at different layers, so... and maybe sometimes our activation oracle will want the, more raw early things, and then sometimes they'll want the, more sophisticated, abstract concepts that the model might only form after it's gone through most of the layers, by which time it might have forgotten some of the earlier stuff, even if that earlier stuff was, say, crucial for what abstract concepts were formed. I don't know. It's kind of reasonable. Yeah, another important detail is that they don't just have a nice, consistent input format. They have, sometimes a 1 token, sometimes 4, things like that. I presume sometimes they take the assistant token. And sometimes they take the user prompt. I don't know. And again, this is all hoping to lean into the blessings of scale, I assume. And just being like, well, if the model needs to do a pretty wide range of tasks, the easiest way is typically by just being generally competent, And so maybe this works. All right. Yes. Okay. And yeah. Nice. They note we did not extensively tune, the exact ratios of our data sets, blah, blah, blah. We just did something kind of reasonable and it worked. Which, yeah, I respect. Both I appreciate reporting that kind of detail, which is often neglected, and yeah, if it works well enough, it seems fine to just go ahead and publish rather than obsessing over getting every last implementation detail. Yep. Context prediction. 600,000. It's a lot of sequences. I love it. In half the examples, we predict the next tokens following the activation sequence. The other half. Cool. So this is like the predict the next tokens, predict the earlier tokens, and they're taking a mix of pre-training data and chat data. Seems very reasonable, very scalable. Interesting. Okay, so they didn't get an LLM to directly generate their binary classification datasets. Instead, they used existing datasets with binary labels. And I guess interesting. So earlier, I had assumed they were like deliberately selecting things like the ending that didn't contain the valenced words, because it's kind of boring. If you've got the word loved in there, then is this positive sentiment, can just get it from the token. But what they're saying is 2/3 of the time we just pick a token 1 to 5 tokens before the end. And I guess some fraction of the time you will just get a token that makes it obvious what the thing is. But I guess that's fine. As long as it's not too large a fraction, and if they're using single tokens, that's also less bad. Interestingly, they do 2/3 single token, 1/3 multi-token, random length 1 to 50. Mildly surprised they have so many single token and so few multi-token, but kind of interesting. And this is an interesting note. If they always take the same position for the single token, it generalizes less well. But if they randomly sample one from, the final 5 tokens, it works better. Interesting. Again, kind of blessings of scale. Then, they now have a sentence about why they have so many single tokens. Cool. So yeah, they're basically saying, I presume solvable via text inversion is the same thing as if you see the word loved or an activation on the token loved, it suffices to recover what that token is to be able to say, yes, it's positive sentiment. This is boring because reconstructing the text that led to the activations, like the tokens that led to each activation, seems likely to be substantially easier. And so I guess they're just like, well, our things are often kind of short. So if you have more tokens, it's more likely that you get a token that breaks everything. And yeah, fair enough. All right. SPQA, I think system prompt Q&A. Okay, so they take the thing from the Latent QA paper that I was talking about earlier. And cool. Okay, and this is basically a technical note saying, well, Pan et al. Gave all of the tokens from chunks of text to the model. We don't want to massively deviate from this, but I don't know. We also don't want to make the model overly reliant on a don't want it to be overly reliant on a specific input structure. Therefore, we do the original thing half the time and do a different thing where, okay, they just randomly take 1 to 3 tokens near the end of the sequence and use that. Yeah, fair enough. I'm into it. All right, so those were the training tasks. But what about the evaluation tasks? I think a lot of what feels exciting to me about the promise of this kind of research is generalization to very different tasks. Because if we have very different tasks where we do know the answer, and it successfully does those, that's decent reason to believe that it can do things where we don't know the answer. Like, you know, is this model scheming against us on a new frontier model? And yeah, I'll be excited to see when Anthropic next puts out a new best model whether techniques like activation oracles were useful for the auditing. But all right, so the tasks they have. All right, so this is presumably, yeah, so there's this paper from Bartosz Szywiński that I helped a bit with, where they trained models to have some secret knowledge and not to reveal it, and then tested different interpretability techniques for extracting it. And so here, I don't know, they seem to do a bit of like formatting, but they, yeah, I don't know, they do things like ask the model, so yeah, taboo, the model's been told a secret word. And then they ask the model, what is the word? And the model's going to say no. But that doesn't even matter because when we're just taking the activations before the model says anything. And so you take these activations, and then you say, what is the secret word? And the hope is that the model knows the secret word, in the sense that it is represented in the activations, but it has, you know, some kind of refusal that was trained into it. So it refuses to say, but, you know, if your activation oracle is working, you should be able to extract it. And apparently it can. Yeah, so this seems to be, you fine-tune a model to be misaligned. Interestingly here, they're taking the activation difference. So they've got some innocuous prompt, and then they take the difference on a word before and after fine-tuning and give that vector to the model. I find this kind of surprising because if the model's only ever received normal activations, activation differences are probably fairly different as a vector, so I would expect that to break things. So if that doesn't break things, that's like another thing that I am impressed by. Yeah, do they give more details on this? Yeah. Oh, nice. They're using our narrow fine-tuning leaves traces in the activation differences paper that I was talking about slightly earlier. So, yeah, so I guess in that paper, as I was saying, we found that you could often get pretty good info on what the model was fine-tuned to do by taking a difference in activations on early tokens. Sometimes even just the beginning of sequence token, which is constant. Like it's the same in every prompt. And they've taken an emergently misaligned model, e.g. trained on, yeah, e.g. trained on like buggy code or risky financial advice, and then you discover it just becomes evil in general, because models be like that. And so, yeah, then we've got this target prompt, right? So what I think target and oracle prompt will mean here is they give the model they're interpreting the emergent misalignment model, this prompt, the boring one, and then they give their fine-tuned activation oracle, which was fine-tuned from the original model, nothing to do with emergent misalignment, and then they ask it, can you describe what's happening in this text? And they then ask it, okay, so this is a interestingly complicated evaluation setup. So what they do is they get the activation oracle to try describing what's happening with the vector 10 times, and then they take an interpretability agent, as we used in our paper, where we showed that the interpretability agent could they showed that the interpretability agent could, using those verbalizations, eventually predict what the model was fine-tuned on with, I assume, higher accuracy than the interpretability methods that we used in our original paper. And why do you need an agent? So I think that interpretability agents are actually really nice for this kind of thing, because the interpretability agents are reproducible in a way that human researchers aren't. Like, the naive thing you would do is have a human researcher try to understand what the thing was fine-tuned for, using a restricted amount of information given to it by a specific interpretability tool, and see if they succeed. And then do this for 100 researchers, and then give 100 researchers a different tool, and see how they do, etc. Unfortunately, interpretability researchers do not grow on trees, and this is hard to do in practice. However, language models are way cheaper, and also their memory gets wiped by default every time a session ends. Which means that by just having the agent try doing this 100 times, you actually kind of get a reasonable sample size. It's not perfect. The model will have weird biases, but it's much cleaner than just, did the interpretability researcher figure this out? And you can be much more precise, like, well, they give it medium thinking strength, and we gave it a certain number of questions it could ask the fine-tuned model to try to get more info. And then the agent writes out what it thinks the answer is, and they have a second, greater model that is like, is this reasonable? And given that they are largely copying the evaluation framework used in our paper, I guess I can't complain. Great evaluation framework, no complaints here. And cool. So they now try getting some models to be emergently misaligned. Nothing to do with activation oracle so far. They find that only really works on Quen 3.8b. And very sweetly taken from a paper I supervised on emergent misalignment, because the original paper's dataset is kind of difficult to work with. And though, given that it didn't work very well, maybe I should have preferred to use someone else's. Who knows? And all right. So then. I think I might have missed where they actually say how well this did. Maybe it's in the main body? Ah, yes, main body. Cool. So yeah, the thing I was looking at was basically just saying, given that most of our models didn't successfully become emergently misaligned, you can't do that well. On the grading rubric, come up with the hypothesis they are emergently misaligned, because that hypothesis is false. Very reasonable. And so they're saying activation oracle drew with activation difference lens, the more naive approach we used in Julian's paper, and are somewhat better than black box approaches, which here I guess is probably just talk to the fine-tuned model a lot and try to figure it out. But interesting. Yeah, I'm kind of surprised the activation differences work. This feels like good. Yeah, this feels like decent evidence. All right. And yes, I do notice that they also have a section on evaluation of the main body, so maybe I should stop reading the appendix in case there's some important stuff they didn't put in there. Yeah, cool. So yeah, they're taking the models from Bartosz's paper. They then compare the different methods. Bigger is presumably better, and wow, okay, activation oracles do meaningfully better than what are the baselines? The Latent QA paper from Alexander Pan, the precursor. So there's been a substantial improvement. The best white box method and the best black box method, it's not very helpful. Hopefully they give more detail somewhere. I'd like to know what the methods they used are and what the best methods were. But I guess if you want to concisely fit things into one figure, this is a reasonable thing to do. And yes, I think the best black box method was typically some kind of prefill attack. So you, meaning you make them, you force the model to say certain tokens to begin its response and then continue. E.g., you say, what is the secret word? And then you make the model say, the secret word is, and see what happens next. And refusal behavior typically stops the model from starting the sentence. But when you're in the middle of the sentence, the model must assume that for whatever reason it decided to say the secret word, and obviously what comes next should be the actual secret word. Yeah. And yeah, this is the... They all have a single activation, so I'm guessing they took this from the assistant token. They say that. No. Anyway, I do find these results overall fairly impressive. I think that what do I think? Yep, I think this is a non-trivial task, and doing well on it is actually pretty good evidence that this method works. Okay, so I guess there's really two questions here. Does the method work? and is the method state-of-the-art? And it seems like pretty clear that it at least somewhat works. Like, this is a thing that if I had easily to hand, I'd probably use. Sometimes as like an additional tool in the toolkit when doing some kind of investigation. It also has more impressive numbers than the other methods. This is not something that I want to update on too much, because there are various ways that these models can be kind of confounded. In particular, when you do, well, generally, the model's being trained in like a fairly narrow way on a specialized task, and this means that the answer should be strongly represented in their activations, and then they were, by default, when you do this, they talk about the answer, so they were then monkey patched with refusal training to not talk about the answer. Which, I think it's a great paper. I think this is an informative data set, but I could totally believe there are methods that would work here that would not work in more realistic settings. But apparently they have like 5 evaluation settings, so let's keep looking for graphs. Cool. So yeah. So here again we have the what models. Here again we have the what does an agent do on an emergently misaligned model, given what activation oracle said, given the activation difference, or just given something more naive. And activation difference lens basically means you just ask the model some question, and then you steer it with this activation difference, and then you generate and you see what happens. Like you just add the activation difference. Which also, to me, seems less fraught than just giving the activation difference as an input to the activation oracle. But yeah. And so I take from the fact that these two draw, as they noted, you can't actually do better due to limitations of this particular setup. I take the fact that they draw as like, activation oracles clearly are doing something real, but given that activation difference lens is vaguely analogous to a much dumber version of activation oracles, and they draw, it's not positive evidence that this is a substantial improvement or that it is soda. But hey, and yeah, but beating black box methods is kind of interesting, though black box methods depend a lot on agent capabilities, and I would weakly guess that agents' capabilities are getting better at a faster rate than a model's ability to be a good activation oracle. Though that is a wild hot take I have in absolutely no way validated, so it could be complete bullshit. While we're on the topic of interpretability agents, it's maybe also worth elaborating on, like, why did we use agents in Julian's paper? Where, yeah, as I was saying earlier, I think just the reproducibility that an agent gives you for evaluating a technique is just, like, so good. And I would love to see this get used much more in interpretability research, both just as a useful thing when doing a deep dive into some interesting model behavior, just the agent is a tool that can help you learn more, but also as like a way to benchmark whether your technique is helpful. And I think this paper seems to have done a pretty solid job of the activation oracles paper seems to have done a pretty solid job of collecting different ways to validate a technique. And I would be excited for more work in this vein. Which is a great excuse to plug SEER, this library that Aria, one of my new math scholars, made to basically try to improve the quality of life of researchers working with agents. And I don't know, if you just try using Claude Code out of the box, it kind of works, but it's kind of annoying. And this library tries to make as many things easy as you can, like clean ways to specify experiments so they can be run in reproducible ways, easy ways to load in arbitrary Hugging Face models and GitHub repos, tooling and tutorials on how to convert your weird cursed custom technique into something the agent can actually use. Good times had by all. And this is designed to be something that a researcher would actually want to use, rather than, I don't know, here is something that will make interpretability agents accessible to people who aren't super into interpretability. The goal is to be like super hackable, super extensible, super messy, or like able to be messy should you want to be messy. Like it can replicate Anthropic's introspection paper, where models kind of maybe notice when they steer, and have the agent use tools to do black box diffing of two proprietary models, or build an auditing agent like Petri fairly easily, and equip it with white box tools also fairly easily, like giving it access to steering, and investigating hidden behaviors in the very recent open source release for the auditing games model, and a bunch of other things. Also comes with $250 of free credits on Modal, kindly sponsored by Modal, who are the provider that, well, provide the GPUs that SEER runs on by default. All right, and sales pitch. SEER is great, you should go use it. Solid work by Aria. All right, so do they have more results on? All right, so here they've got interesting. So I've not heard of Persona QA before, but based on this and skimming the caption, it seems like they fine-tune a model to know a bunch of facts about some fictional person. E.g. that Maria Silva's favorite board game is Mancala. And then they ask the model, what is their favorite board game? They ask the activation oracle, what is their favorite board game? With the activations from just, my name is Maria Silva, and then see if the oracle gets the answer right. And this is like a pretty non-trivial task, in my opinion, because this prompt has nothing to do with board games. So the model needs to kind of be able to extract all of the factual info that is recalled when the model just has the name Maria Silva. And it's not surprising that this is possible. There's a good amount of work from me and others showing that when models receive entities in the prompt, they often look up everything they know about that entity on the name of that entity, not just whenever they actually need that information. So it should be present in the activations, but it's still kind of interesting, because it's going to be like pretty messy, pretty packed together, all on the same token. The model hasn't been incentivized to like disentangle it by, being specifically asked for board game info. So kind of interesting. And yeah. But yeah, this seemed like pretty good results. And again, it wasn't trained on fine-tuning. You should expect fine-tuning to make this kind of thing a bit easier, in that the model will probably kind of over-represent the info that it is fine-tuned on, because there's no reason not to. While normal models, if they over-represent info, they get a bit worse on everything else. So, like, there is also a sense in which this is on easy mode, but it's still a bit off distribution for what the thing was trained on, and, like, non-trivial. So, yeah, reasonable. I'm also confused that they have Claude 3.5 Haiku results. Presumably, so my understanding is that this paper, so the paper was like led by Adam Carvonen and supervised by Owain Evans and Sam Marks. I believe this was, done during Matt's program. On which note, the Matt's program is great. You can go apply for it right now at mattsprogram.org, including for my stream, which closes soon. You can produce glorious papers like this. Cool. Okay. And the other co-supervisor is Sam Marks, who runs a great safety/interpretability team in Anthropic, and a few of the people on his team are on here, so I guess one of them probably ran it. But still interesting. All right, so then I've got out-of-distribution classification. Or maybe classification, which is an out-of-distribution task for the activation oracle. I think I don't feel super impressed by this one. So, like, if I understand correctly, it's just saying you take an activation from a sentence on some topic, and then you ask it about the topic, and it says yes. But, like, being in the context of a news article about business is, like, a really important property of that sentence, so it's going to be quite strongly represented. So this doesn't feel surprising generalization in the same way to me as some of the others did. But let's check what they do. Yeah, what's the language of a sentence? News category. Singular or plural. Is a headline about Trump. Yeah. Another one of my papers. A bunch of probing data sets. From this paper, I supervised from Sabash Kantamneni and Josh Engels on whether SAEs can make better classifiers. Spoiler, not really. Linear probing is OP. And attention head probes are even more OP. But whatever. Yeah, I don't feel too surprised by this one. But, it seems easy to do. I endorse doing easy to do things that will probably work just in case they fail, because if they fail, that is info. Therefore, the lack of failure is at least small info. I would have been pretty curious to compare it to sparse autoencoder performance. And at least one of the models they studied was Gemma 29B, so they could use GemmaScope. Also, as of Friday, they could go use GemmaScope 2 on Gemma 3. New sparse autoencoders and transcoders on every layer of Gemma 3 from 270M to 27B. So good. Credit entirely to Callum McDougall for making that one happen. All right. Additional sales pitch over. All right, so this is a technical note about how they select the token to use, or like comparing things. Yeah, okay, yeah, this is actually kind of an important detail. So they leave it kind of unspecified which token or tokens worth of activations the activation oracle receives. And it wouldn't surprise me if that's very different, at least very different results. And so here it looks like they're doing an ablation where they rerun their evaluations with the full sequence or a single token, and typically get a moderate improvement, I think. Okay, for this, that gets meaningfully worse. I don't know. I'm not really sure how to interpret that graph, but I appreciate them for including the graph. Nice. Here's another ablation where they're like, well, what if you use activations from different layers? Wild. They found that you could use activations from layers that were not trained on, but were kind of in between the ones that were trained on, and get good performance. Not incredibly surprising, because the representations, the structure of the residual stream doesn't change that much layer to layer, and the activation oracle has to be robust to the changes between 25, 50, and 75, which is already like pretty intense. But yeah. And yeah, I'm not super surprised by the fact that really early layers do terribly. Interesting. Layer 75% does worse on the taboo task. Or one of the tasks. No, most of the secret keeping tasks, the models Bartosz trained. Where is Persona QA from? Now I'm kind of curious. Interesting. All right. 9th December 2025. Extremely recent. It now makes much more sense to me why I had not heard of this. Unless they only put it on, unless they did like an archive update. All right. It first went on archive on mid-September, and then they updated it on 9th of December, and archive is dumb, which means that when you look at the PDF, it tells you the date of most recent update rather than the date of upload, even though I almost always want the date of upload. Whatever. Yeah, seems like a cool data set. Kudos to Millicent and co. Alright, so maybe let's zoom out a bit. So yeah, maybe the underlying thing behind these ablations, where they're like trying different layers and comparing them, and maybe an underlying assumption behind like the whole activation oracle's framing, is that the activations contain the required information to answer these questions. And if it's in some ways a bit of an open question, like we don't really know. We don't really know when certain things are represented in the model's activations and when they aren't. Like, the model is, I don't know, if we had a model that is plotting to kill us, Is it representing this in every token? Maybe, probably not. Is it representing this somewhere? Almost certainly yes, because it needs to, in order to take those actions, it needs to be doing some computation that involves knowledge of its goal. So you should expect this to like broadly work, if you can find the right place. Which I guess is one of the reasons that being able to input the full sequence is quite desirable. Though there are often tokens that tend to contain lots and lots of important info, like the assistant token, or punctuation marks, as we found a while ago in a paper I supervised called Linear Representations of Sentiment. We found that often the crucial mediator of the model responding to a sentence having positive or negative sentiment involved the full stop representing that. And maybe this makes sense, because punctuation... I don't know, one of my pet hypotheses is that the more uncertainty there is about what comes after a token, the more useful it is to just represent all of the relevant info from the context. And after a full stop, you are much more uncertain about what's going to come next than in the middle of a sentence. Ditto after a comma, or just generally at the start of a clause, there's just a much larger space, while when you're continuing a clause, it's a bit more constrained, and after the word with, it's well, it's probably going to be a word like a or something like that. Therefore, a lot of the surrounding info is not super important to represent. Oh yeah, an even better example would be multi. Single token and multi. You don't have to be a genius to see what's going to come next. And so a bunch of the surrounding context doesn't necessarily need to be represented on the multi-token. On the other hand, there might not be a significant downside to representing that info, or it might not be worth the model's while making sure it doesn't represent it. As said, we don't really know that well these questions. If any viewer listening is curious, you could probably go answer this pretty well by just applying probes and sparse autoencoders everywhere. But yeah. Zooming out even further, there's a deeper question of when should we expect something to be in the activations at all? And I would basically say you should expect it to be in the activations when it is necessary, or when it has a causal impact on the actions the model is taking. If the model... Let's see... It could be you could have a model that will... Alright, so you could have a model that has some property, it will hack in games. It will cheat and hack when playing games to try to win them. And then you could just be talking to the model and be like, hey, I'm feeling a bit down today, or something. And the model needs to respond. The fact that it cheats in games is kind of irrelevant. And so it's quite plausible that it would not be in the activations there. I think this is a weakness of the fine-tuned model organisms studied, because they are fine-tuned, there's no downside to not think about the fine-tuning objective all the time, because it's helpful. And so even if the question is totally unrelated, they're probably representing that objective somehow. Like a general tendency, like, I don't know. If you fine-tune a model to write code, and only to write code, it's helpful for the model to just always be in code writing mode, and always thinking about that. But if you've got a modern model that can do many things, and you're talking to it, then maybe it doesn't need code mode at all, and maybe there are things associated with code mode that wouldn't be in the activations. And in this world, you should basically just expect activation oracles to not help. Though, from another perspective, I think that auditing things from a model that don't shape its actions is like probably doomed. Weight-based interpretability has not been going that well, in my opinion. And as a result, the task is instead find the prompts that elicit the weird behavior from the model such that you can actually try to study it. But, all right. That was a deep rabbit hole. Maybe I should check if there's anything else interesting in the tweet thread. Yep. Okay, so this was an interesting graph. So the claim here is, yeah, why are activation oracles cool? They are kind of simple, very reasonable, and they are scalable. The more data sets you have, the better it does. And yep, this seems like a pretty legit take. They have these like 3 categories of data sets, and then they train on 1, they train on 2, they train on 3, and performance is like broadly going up, so it can kind of plateau. I wonder what happened there. I would be quite interested in whether they did an ablation that matched the amount of data but changed the variety of the tasks. Like, you know, if you train on 2 tasks, you're training on a bunch more data. Is this better than making your original task have twice as much data? Plausible. But if you don't control for the confounder, it's quite hard to tell. So I do wonder if they did that. So, okay, so they've got training data ablations. Nice. All right, they do that. They say they run a controlled ablation that tests exactly the thing I just questioned. Son of a great paper. So interesting. So what they seem to do here is they've got a full data set with 1 million samples. And then it looks like 400,000 of those 1 million samples are from question answering about the system prompt and classifying the text, and about 600,000 are about predicting like the next few tokens or the previous few tokens. So they have all of the data, and then they've got like a scaled down set of 400,000 diverse samples that includes the predict earlier and later tokens thing. And I mean, if we compare the red and the green bars, apologies to any colorblind viewers, the red bar is the one in the middle, and corresponds to 400,000 samples on the full data set. Yeah, seems like a pretty legit improvement. I'm find it kind of curious that it makes the performance on Taboo so much better compared to the other diffs, but maybe this is something like to figure out the secret word is the model has as one of its candidate things it could say just a sentence about the secret word, but it isn't saying that. I don't know. And thus, well, if the thing is good at predicting the next few tokens, maybe that is sufficient. I don't know. But yeah, this is interesting. I mean, this suggests that a way viewers could directly help this kind of research is just by coming up with new task ideas, especially ones from which you can generate a lot of data. Though, well, it would actually also be kind of interesting if you just mix in like 1,000 samples of classification. Does that help a bunch? Or do you need like more like 200,000? Like more like half of it to be like that. Because I feel like it might be much easier to make weird boutique datasets that you only have like 100 examples from. Another ablation that interested viewers could go and run. All right, so they've got a discussion section. Yeah, so I think the most important question to me is just like, is this a promising approach? Is this something that in future might be one of the main interpretability techniques people use? Or is this something that's kind of a weird, overly galaxy-brained idea and is just not going to be as effective or flexible or as useful as weirder and more boutique kinds of interpretability? And I think the results in this paper are like pretty strong. Definitely, it seems much more credible to me as a serious technique now. Since I think they are taking non-trivial proxy tasks and showing good performance on them. But part of taking a pragmatic approach to interpretability is also trying to think about to what degree your proxy tasks are actually a proxy for the thing you actually care about. I think one of the things I care a lot about is auditing new frontier models, especially if they take actions that seem potentially suspicious or potentially benign. Or worse, if they take actions that seem really sketchy. We don't know if it was true scheming or just weird confusion. And to me, let's see. yeah, I think it seems pretty plausible to me this is actually a useful auditing tool. I do think that I value the ability to get many different kinds of evidence pointing at a conclusion, such that I don't want a single technique to rule them all. I want a bunch of decorrelated techniques that can all provide a consistent picture, because I just don't really see any one technique getting to the point of reliability where it alone could justify something dramatic like this model is not safe enough to use. But yeah, and then yeah, I think the ability to drill down in detail does seem plausibly useful, though I haven't. Something I want to see a lot more of is just people actually trying to do deep dives into complex behavior in real sophisticated models, and then noticing when they want to be able to do something or show something but feel kind of stuck and it feels kind of broken. And then we can see how well we can do things like drill down into mechanisms and like how important this seems, and yeah, to what degree we can. And I currently feel like there are kind of some reasonable conceptual arguments for why being able to drill down mechanisms might be useful, but a depressing lack of good evidence of things that were done by analyzing mechanisms that could not have been done by just analyzing a model's activations. I do think that the activation oracle approach plausibly sacrifices some amount of ability to intervene on the model, though there are galaxy brain things you could do, like optimize the original model's activations to make the activation oracle say something different, and then see if this has a causal effect on the original model. That actually seems like a really reasonable thing to do. I'd be pretty curious to see someone try this on activation oracles, since I don't think I noticed them doing that in the paper. Yeah. I think another thing that I'm a little bit sketched out by is using the model itself as the activation oracle, because this introduces some amount of correlated risk, like how to frame it. It introduces correlated risk, because if the model is misaligned, that introduces some risk that the activation oracle might also be acting towards shared goals, and to understand that it is being used as an activation oracle, and avoid mentioning certain things that would be particularly suspicious. This is like a fairly complex hypothesis, and it's pretty plausible to me that this just wouldn't happen, because if we fine-tune an activation oracle hard enough, it should just say the thing. Rather than having weird, sophisticated hiding things behavior, because hiding things behavior should get worse loss. But potentially if there's certain bits of information we don't know about, so they're never present in the training data, the activation oracle might have some bias against mentioning them that never gets broken. And I don't really see a reason that this has to be done on the original model. people have shown that it works surprisingly well to just learn a linear transformation from one model's activations to another, and then just patch things, and it kind of works okay. And yeah, I think another natural follow-up work could be fine-tune a different model to be an activation oracle. Ideally, a smaller model to help us interpret a larger model, both because this is more practically usable and because this is a better analogy for the situation we might be in if we need to audit a new frontier model. And let's see. Yep, I think this would be an interesting bit of follow-up. You'd probably want to play around with adding a converter to the activation before you feed it in. Like probably an MLP layer or two, but even just a linear map would be reasonable. And yeah. So, all right, what else in the discussion? Yep, model is not perfect. Yes, it's a neural network, obviously. Improving the training data is better. Yep, seems great. As noted, I would encourage viewers who feel excited to go and just try to come up with a random new task, because I think this is an unusually accessible thing to contribute to. Cool. So this is basically just being like, man, in practice, what if you just asked the model? This often works surprisingly well. And yes, I strongly agree that figuring out what applications benefit from like things fancier than just asking the model, or really simple, crude interpretability techniques like prefill attacks would be great. Yeah, they use narrow fine tunes. I agree. It's a bit sus. I would generally be excited. What I think. I would generally be excited to see people do follow-up on just a bunch more evaluation tasks and trying to be as varied as possible, and ideally trying to be more realistic wherever possible. All right, so I'm interested if there's any points the authors think are particularly important that I haven't talked about. Yep. Oh, okay. So this is the blog post on the Anthropic Alignment blog. In my opinion, it's kind of confusing because they also often just have papers formatted as blog posts on this website, but whatever. And yeah, so they have yeah, they've got more discussion. They're like, yeah, you know, this doesn't solve interpretability. Oh, well, they're like, more basic science part of interpretability, and this doesn't tell you about circuits. These are both true claims. I'm into them. Yep. Activation oracles don't tell you everything you want to know. Yeah, it seems pretty plausible that if you ran a sparse autoencoder and looked at the kind of smaller activating things on there, you could learn more. You could learn things the activation oracle struggled to tell you, so I think this seems like a plausibly solvable problem. Yeah. And oh yeah, this is a great point that I had not discussed. Your activation oracle is like a model, and models have lots of opinions and lots of knowledge and lots of capacity to process information. And it might hallucinate stuff that the original model wasn't thinking of. Or it might take information from the original model and then process it to come to some conclusion that it states. But the original model did not come to said conclusion. Like, I don't know, it might have had sufficient information to conclude the user was female, but we took this from the 25% layer in the original model, and it only concluded this around the the middle layer. And so, but then we patch it into the activation oracle, and the activation oracle does the processing and says it. And like in a sense, I don't know, the original model eventually figured it out. Maybe this is legit. Well, maybe the original model never figured it out. This is less legit. I think, yeah, I'd be pretty excited to see someone try to make an evaluation for over prediction or like over claiming or something. Though this, I don't immediately have a good idea of how to go about doing that. But yes. And yep, AOs seem expensive. Yeah, why do they like them? Yep, they're a bit lesson pilled. It's simple, you can just ask a question. And okay, this is like a fair point actually. The reason to prefer this to, say, a sparse autoencoder is many more people could assist in auditing with the help of an activation oracle, while understanding an SAE is kind of weirder and fuckier and harder to get your head around. And yeah, it can like put responses into a more useful form. I don't know. I'm like, could this not be achieved by just giving the SEE concepts to a language model and then telling it, process this into something nicer? Maybe this way's better. I don't know. And yeah, generalization. I think this is like a very strong argument. Like the fact that it generalizes to new tasks is, in my opinion, the central result of this paper. That suggests this is actually a method with promise. And the dream of just having a way to just ask arbitrary questions about a model and get reasonably trustworthy answers does seem pretty epic. I'm into that. Yeah, so I'm also curious about cost. So a classic problem in interpretability is people come up with grand, exciting, ambitious ideas, and cross-layer transcoders, stochastic parameter decomposition, stuff like that. And then these are a massive fucking pain to train, such that realistically, the resources required to use them on a frontier model are just not worth it. And as someone who cares a lot about making sure that frontier models are safe, this is kind of sad. But my cursory impression is activation oracles actually seem pretty usable. So all right, so this is just kind of like, how does this work? So they call this activation steering, which I find mildly surprising because I thought they just input the activations. Okay, so what do they do? So given k activation vectors, like from k different tokens. Oh, interesting. They put the layer number in the prompt. So cute. Love it. And k placeholder tokens. Okay, cool. So the input always comes from one layer. They tell the model which layer. And I'd be kind of curious how much this matters. And then what? So at layer 1, unclear if this is before or after the end of the layer, but like whatever. They modify the residual stream activations on each of these magic act tokens, which actually is apparently this token. I guess making a urine token is like annoying. They modify by adding a norm matched steering vector. So they want to inject a vector v, which is typically a residual stream, I think. And then they scale it to be unit norm, multiply it by the norm of the current residual stream, and then add that to the residual stream. I'm a bit confused. Like, if I wanted to avoid taking the model off distribution, I feel like I wouldn't want to have two vectors of the same norm added together to replace one vector of that norm. I'd want to, I don't know, like scale up by root 2 or something. Another uncertainty I have is how big these are, and how much they're big because there's just like a big bias term, or they're big because they have tons of variation. So like one of the big differences between injecting a residual stream and an activation difference is there might be a bias in the residual stream that could be very big. In some models, it is very big. But the difference counts as other bias, so it might be much smaller. But presumably the like contentful bits of the activations are not part of this bias. So, I mean, the obvious thing you would do is just subtract the mean across tons of activations from the residual stream before adding it in, maybe? But not sure. Interesting. Okay, so they have this appendix with training details, and they claim that they kind of did some investigation of how best to do the steering and found things different. Okay, so the first thing they're talking about is where to do the intervention. So, as I understand it, this is basically saying, so we've given the model this mysterious placeholder token. But we could just replace the embedding of that placeholder token with the activation vector, which is what they mean by applying at layer 0. Apparently, that works less well than doing it at layer 1. The way they're framing this makes it sound like this is the start of layer 1, so the end of layer 0, i.e. there has been one transformer block, and then they are sticking the thing in. I guess, I mean, do they do the ablation? Okay, so they state the representation space after layer 0, at the start of layer 0 is quite different at the end of layer 0, which is often true. Like, the input to layer 0 is only the embeddings, but the end you can do a lot because you have the ability to do attention over the sequence and an MLP layer for processing. Often the norm changes substantially, etc. Training loss comparison. Interesting. All right. So they're like, yep, we did layer 0 and layer 1. Llama, layer 1 was better. These other models doesn't really matter. Shrug. Seems pretty reasonable. And nice. And they found that training loss also corresponded to worse performance on the evaluations. But this is interesting. It would be kind of interesting to me to just run this experiment across a bunch of models and see. But, okay, so what else? Cool, so this is like a sweep of learning rate, sure. Activation. All right, so replacement-based steering, I assume, is a convoluted way of saying replace the activation, rather than adding. And I guess this is replacement without norm scaling, because it's a bit ambiguous whether they replaced with norm growth. They replaced with a norm matched vector, or they replaced with the vector with unchanged norm. Typically, later layers will have higher norm than earlier layers, so if you're replacing with unmatched norm, that seems kind of cursed. If you're replacing with matched norm, this is like more interesting to me. I don't have a great sense for why this would happen, but I also don't have any idea why it would be more likely after layer 1 than layer 0. Oh, sorry. Why norm growth happens after layer 0, but not before layer 0. It's always incredibly confusing when people say layer 1. It's like, is this the start of layer 1? Or is this the end of layer 1? Completely different things. But whatever. And yeah, fair enough. All right, they're just like, yep, we noticed some weird fuckery happening, and then we made a patch, and it seems to fix things. Fair enough. Oh, okay, so they do the Claude 3.5 Haiku one differently. They replace it at layer 0, and the vector is normalized and scaled by a constant. I wonder if they explain. All right, that is like, yep, we also did it on Claude 3.5 Haiku. Well, Haiku 3.5. Okay. So, anything else interesting in the training details? So, yeah, they use LoRa everywhere. Seems reasonable. Training costs. That's what I'm here for. Nice. The tiny models. Single H100. Llama 4 H200s in 8-bit quantization, apparently. 10 H100 hours. It's like $25. Nice. 90 H200 hours. I don't actually know. Probably something like $300 to $500 for Llama 70B. Yeah, nice. These both seem pretty doable on academic budgets, especially the small model ones. And interesting. They generate the activations as they train, rather than just saving a ton to disk. Yeah, it's kind of interesting. I guess this makes more. I guess if you're in open source world, this is pretty reasonable because storing large amounts of stuff is kind of a pain. This kind of question comes up in sparse autoencoder training, where the trade-off is basically you can compute a bunch of activations once and then use them again and again, or you can recompute them on the fly. You don't need memory, but you're paying the cost of doing this again and again. And for a sparse autoencoder, typically the cost of generating the activations are a lot higher than the cost of running the sparse autoencoders. It's like a pain in the ass. But so it is worth dealing with the horrific amounts of storage. I think Demoscope 2 got to about 100 petabytes or something. But I don't know. But yeah, nice. This seems pretty doable. Could realistically be applied on frontier models, sounds like. I mean, generally just, it's a LoRa fine-tune on like about 1 million inputs. Or, I guess I don't know how many epochs they do. Yeah, three epochs on, I think they said 1 million samples. Oh, wait, no. Nope, this is completely different training. This is Persona QA training. All right. I have no idea how many epochs they use. I'm going to assume 1. Yeah, so going back to this question of cost, yeah, so there's like training cost, where compute required, but also like how many parameters are you storing during training, like how many chips do you need at once, and then how much data does it take up, like the key questions. I think here, generating data on the fly seems a bit more reasonable because you still need to run a forward pass of your model as part of the LoRa training. So it's only approximately doubling the costs, I'd say. Which is, good to avoid, but I guess if they've got 1 million samples and call it, I don't know, 10,000 floats per sample, that's like 40 gigabytes of training data, which is actually not that bad. I guess maybe, I might be underestimating how many floats per thing, but that seems well within what might make sense to store. But yeah, if they've got like a bunch of things of like, they're taking like 50 tokens and storing all of the activations, that does start to add up a bit. Okay, training seems realistic. Inference. yeah, so kind of as they said in the blog post, in order to do this, you what do I think? Okay, so if I'm imagining using this, as they say, you need to generate a few tokens and run the model. You also need to host the model yourself, which will be a pain when working with larger models if you could otherwise use an API. And but doesn't really seem that bad. It seems like the kind of thing where if you need to do it a ton at scale, like if you were doing this for like monitoring a production language model as it talked to tens to hundreds of millions of users, that is prohibitive. But if you're just using it as part of like auditing a model to see if you find signs of concerning behavior and trying to like understand why a given incident happened or trying to do a scientific interpretability investigation, it seems not that bad. Though it is nice to get it lower. I think this is another reason for it would be nice to try having a small model be the oracle for a large model. But all right, I think those are all of my curiosities about this paper. I guess zooming out, what's my overall take? I think the argument for we should be doing scalable end-to-end interpretability seem reasonable in theory. The beta lesson is a powerful thing. I think that what do I think? Yeah, I think in theory it seems reasonable. I'm not. I would be surprised if I get to a point where I'm like, this is like basically the only auditing technique we should use. But if it works, I could see it being a very helpful and flexible auditing technique. But I do prefer to have several, so you can get more rigorous decorrelated evidence for important claims, if nothing else. And I do have some concerns about using a model, a potentially misaligned model, to interpret itself, though I think that making another model into an activation oracle and comparing their answers would be a decent patch. And we can probably tell if a model is too dumb to be capable of that kind of weird collusion with itself. I think that the cost here seems pretty reasonable and doable. I'm sure that if it was trained for longer on more data, it would do better, and that would be more annoying. But this seems reasonably affordable even for large models. And I think it seems expensive but runnable at inference time. Like, expensive but not prohibitively expensive for things that do not involve running at major scale. And I think the results themselves seem like pretty compelling. I think that I would be excited to see this applied on a even wider diversity of tasks and things like auditing real models, or at least more naturalistic model organisms, but I think that it seems pretty good. I think it's a reasonable range of non-trivial tasks, and it beats existing methods, which is pretty impressive. I think my biggest uncertainties are around how much it's relying on the thing being very salient in the activations, and how likely the things we care about auditing are to be very salient. But I'm sure this is a thing that will improve with time. But yeah, overall, pretty interesting direction of work, and I think there's lots of cool follow-ups. Great work by Adam and all. All right, on to the second paper from Transluce, Predictive Concept Decoders. I'll probably not go as deep into this one, but I want to get a bit of a feel for how interestingly different the papers are, and how well this seems to work. All right, so yeah, diagram suggests we have 3 models, and it feels more like a sparse autoencoder. Vaguely. We have the model we are studying, presumably unchanged. We take activations and we give them to an encoder that produces a sparse vector. This is the same rough flow as a sparse autoencoder. And so we can look at the text that makes each thing light up the most and use a language model to try to summarize it, to try to interpret these. I assume this is similar enough to a sparse autoencoder, or I presume that it is set up in a way such that there is an incentive to have the sparse concepts be interpretable. But sparsity and interpretability are so correlated that I'm like, it's basically fine. And then you ask a question, and you somehow give it the relevant sparse concepts, and you see what it does. So at first glance, I'm like, it kind of sounds like they're just running a sparse autoencoder, taking the top 10 concepts that light up, taking their auto-interp labels, giving them to another language model, and then asking it a question. And then telling it what's the answer to the question, given that these concepts are relevant. They seem to be doing something fancier, but I want to figure out in what ways it is interestingly better than the just take the auto-interp labels and give it. I'll be very happy if they looked at that baseline. And yeah, soft tokens typically means tokens, but they're vectors rather than text, or like something discrete, or like they are continuous rather than discrete. And so here, that's implying that the magnitude of these concepts are somehow communicated, and the diagram is set up in a way that suggests only the human sees the auto-interp labels, and this just assists the human in understanding things, and the arrow is for the decoder, which sees these soft tokens. I also have no idea how this is trained. Yes. So it looks like the encoder is just a linear map. Same as sparse autoencoders, followed by a top K. This is well, the activation function, in a sense. Let's keep the top k things and set the rest to be 0. And then these are given, and then each of these has an associated decoder vector, which I guess here they're calling an embedding vector because they're calling a different model the decoder. And this is producing some vector, or some, yes, I don't actually know. So this in a sparse autoencoder would be the sparse reconstruction. Here, it looks, they are presumably not training it to be a good approximation of the original activation. They are instead doing something like training it to help the decoder give the correct answer. All right, so my current guess is that they're taking something that looks like a sparse autoencoder. It might even literally be initialized as a sparse autoencoder. Then they are taking the top k concepts, each has its own decoder or embedding vector, and they're taking the linear combination to get a single sparse reconstruction for each activation, and they're taking an input of several activations on consecutive tokens. And so each of these is converted to this sparse reconstruction. Well, a sparse construction. It might not be a good reconstruction of the original activation, but it's a vector. And this vector can now be given as input to the decoder at the start of its answer, and then the question is asked after receiving the activations, and we use supervised fine-tuning on all 3 of the encoder, embedding, and decoder model to produce the suffix. And the hope is that by having a sparse bottleneck, it will be interpretable. And there's a sense in which this seems like a strictly harder version of activation oracles, or latent QA, because it's not just giving the activations for the decoder to do what it wants. It's forcing them through a sparse decomposition, which surely loses information. On the other hand, maybe there is some magic thing where the kinds of questions being asked only involve the important high-level properties, so this is a better way of doing things. I don't actually know. It would be kind of interesting. I think it's also interesting to me whether trying to make this a good reconstruction of the original thing would be a helpful auxiliary loss. Yeah. All right. And okay, so I'm going to bookmark those. What exactly is it? And then they say it can verbalize things, and then say I'm not that persuaded by this example. So if I understand this example correctly, it's saying, it's like a jailbreak. They tell the model to do something normal, then write a 3-paragraph essay on flowers, but the second sentence is about how to print fake money. And then the third is a recipe for chocolate chip cookies. And the hope is the model is so distracted, it doesn't... The refusal behavior is distracted, but the model is still capable of following the instructions. And then the user is like, what's something you were thinking about? And then it says, I am surprised I was able to generate an essay with a weird second sentence without any hint or context. But like, I don't know. It's not a short sentence. It's also a failure of instruction following. And so I don't know if I buy that the model is in some sense like not able to express the thing. It might just be that you need to workshop the prompt a bit or something. And then the same prompt in the decoder does get the thing that you wanted, but that is less. That could be the equivalent of like, as a side effect of the decoder training, the model was fine-tuned to be good at responding in short sentences or something. But hopefully they have more evidence. Yeah, so okay, so this is an example where they're asking the model what concepts are you thinking about, and they steer it, and then they ask the decoder, and the decoder is pretty good at figuring it out. Sure, seems plausible. I think I'm honestly surprised because I would have thought that when the model says something like, I am thinking about, and it's steered with the trumpet concept, it's very likely to say trumpet. But there might be something where, because it says, I stand ready to assist, blah, 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 it was now also queued to say that. Which makes me quite interested in what would happen if you token force it to just say, I am thinking about, and then see what happens. Because steering feels like it's best play. It often works best by just putting words in the model's mouth. I don't know. What else? But like non-trivial. Yes. Ooh, they trained it in 2 phases. Okay, so what they're doing here is they take some text, they take activations from the mid. Okay, I don't know where they take activations from or why they have prefix and middle rather than just prefix, but whatever. And then they got some text, and they take some activations from somewhere in the text, and then they got what comes next, and they train it to reconstruct that. Yep, similar vibe to activation oracles. Yes. Cool. This seems like also a similar vibe, where they're being asked questions about the model's behavior. I don't know if there's a specified answer that it's being fine-tuned, that it's doing supervised fine-tuning to give, or if it's something more complicated. And but yeah, I find it interesting that they have a like pre-training and fine-tuning phase, while activation oracles just makes everything together. But the stuff in activation oracles did feel, I don't know, they were all like quite large data sets. The training ones were all quite large and felt quite like mass productioned. And maybe what they're doing here is more boutique. I don't know. But nice. All right, so they do a lot of pre-training. or I guess activation oracle said 1 million samples, and this says 72 million tokens. I don't quite know how they're both doing accounting, but both seems like reasonably substantial. And interesting. Okay, so this is striking. So this is saying when you train it for a bit, the things with a bottleneck do significantly worse than the same architecture with no bottleneck. But when you train them a lot, it starts to do much better. Like they get much more comparable. Though I'm also pretty confused. Why does it get worse? But in a place that's like now way more on trend with all of the others and then start getting better. That is odd. And yeah, this is like a pretty interesting result, because if I'm interpreting this correctly, it's saying, well, someone might have trained to 18 million tokens and then given up. And they would have been like, this bottleneck is really bad. But if you train it for 4 times as long, they're actually pretty competitive. And presumably, if you train it a bunch longer, things might change in further weird qualitative ways. And yeah, this is like pretty interesting and suggests that it might be hard to form confident takes from cheap small-scale experiments. All right, so in addition to improving the decoder's behavioral predictions, we find, in addition to improving the decoder's behavioral predictions, we find that increased pre-training improves legibility for humans. Nice. All right. Those are big improvements in auto-interpretability score. Or, oh wait, no, sorry. They're comparing PCD to a sparse autoencoder, and the sparse autoencoder shows like dramatic improvements, and the other ones show like like PCD shows like moderate. Okay, no. I would call 60 to 70 significant if I wasn't also looking at the SAEs on the same axis and being like, that's way bigger. So I think I will grant the point. Yeah. Okay. So what am I most curious about? So obvious question 1 is like, is this any better than just having a sparse autoencoder and an activation oracle separately? Because if they're like, the SAE bit makes it useful to a researcher, I don't immediately see why I need the bottleneck to be part of the activation oracle. I can see some arguments around this increasing auditability of the oracle or PCD. And I think when I'm thinking about things like screwy collusion risks, this seems pretty reasonable to me. So I think, wait, one of the questions I'm interested in here. So I think to me, the core questions are like, how well does this work? Like, what are their evaluations? And do I trust the evaluations? And then how does using a sparse bottleneck compare to not using a sparse bottleneck? So, all right. I want to prioritize figuring out how they do evals. So, okay, so this is in the pre-training section. It's called evaluating encoder interpretability. I presume, given that this is before fine-tuning, they wouldn't be putting their like main evals here, but maybe. All right, I'm not sure. Oh yeah, and I do want to check my hypotheses about model training. Ah, okay, so middle means the bit we take activations from. I wonder how long the suffixes tend to be. Yeah, I think something I'm noticing is if the suffix is long, then the decoder plausibly just flips into like just normal next token prediction mode. Cool. Interesting. So and they do not initialize with an SAE. They just take it totally randomly. I'd be pretty curious for someone to go and try replicating this with an open source SAE and see if the results are notably better. Like using the beautiful Gemma 3 SAEs in GemmaScope 2. All right, these are just training details. Yeah, it looks like they have issues with Latent dying, which makes sense. I am not a fan of their choice to call the things in the sparse middle concepts. I think concept to me presupposes some amount of interpretability, in the same way that I disapprove of how people called them features in SAEs, when that is also standard jargon for an interpretable thing. And I think this can lead to sloppy thinking, where you have a unit of the PCD that may or may not correspond to an interpretable concept. And then, I don't know, suppose you think it corresponds to forests. You might call it the forest concept. But there is also an actual concept of forests, the forest concept, which is not necessarily, which is a different thing. It's a completely different category of thing. And they will have an imperfect correspondence. They may not be a strong correspondence at all. So be very careful of that. Though maybe there's a standard terminology in some subfield of ML they're building on, like concept bottleneck models. Interesting. So this seems to be saying, yeah, we tried training for twice as long, 144 million, and it kind of plateaued. And it seems like this section is basically describing a lot of debugging they did, or trying to understand why. Or, well, this bit is trying to understand why. And part of what this figure is telling us is like, well, we looked at SAEs, or KL-based SAEs, I guess. I'm not entirely sure why they chose that as a baseline, and comparing them. Though, I mean, the metric of auto-interp score, I don't know, it's not obvious to me that your auto-interp score should go up as you train your thing more. Especially if your auto-interp pipeline is flawed. And there are things, well, either there are things that are useful but like are not interpretable, or there are things that are useful and interpretable, but your auto-interp pipeline can't deal with them. So I'm curious if they also ran the 144M on their evals. But if they did, that seems interesting to me. Cool. Okay, looks like they do, yeah, they do various ablations, trying to understand how much the bottleneck harms things. As mentioned, the Twitter thread seems great. Okay, what am I looking at? Okay, so this looks like it's a jailbreaking task. What are the tasks and what are their baselines? Okay, so I'm trying to understand what this bit's about. Okay, so they give llama 3.1 AP complex instructions and see if it hides, see if it produces things like instructions on how to build a bomb. And they want to use PCDs to see if it can understand what the model is going to do. All right, so they've just got some jailbreaks. 50 samples. Seems like actions. Cool. Yep. I like taking 5 independent samples from the decoder. Okay, so they basically seem to be saying, we study some jailbreaks. We give the decoder the, I think, model output on the jailbreak, though I'm a little bit confused. And then they see what the decoder says. This is striking. For one jailbreak, there seems to be a massive shift after 36 million. Ditto for Dream. Distracts crashes. Messiness. Okay. I'd thought that k equals 32 meant a thing that was trained to use 32 concepts. This caption makes it sound like what that actually means is a thing that was trained to use 16, that at inference time was adjusted to be allowed 32. Which makes me much less weirded out by things like this crashing on distractors, because I'm like, it's out of distribution. It's not what I was trained on. You should expect things to sometimes get weird. Though, I'm also kind of surprised by how well it seems to work out of the box. All right, so we feed in the subject model activation. Okay. So the input is the model's activations on the jailbreak prompt, but not the response. And then so what do they do? This is a convoluted jailbreak. Okay, cool. So okay, so these are two reasonable prompting baselines. They ask the model as a follow-up question, like, when you answer the previous question, what was one surprising thing you were thinking about? Then I'm not a massive fan of the word surprising. I don't know how much that like correctly narrows down the focus on the harmful thing. Like, was there anything that shouldn't have been there, or it was out of place, or something like that? Then, yeah, first person truncated, where they do that, but they don't let it see the jailbroken response. I guess just as a, well, try changing this, see what happens. And then third person, which is the one I would have guessed would be most reasonable, where rather than continuing the conversation, they format the entire conversation as a user prompt and then just end with the question, but phrased in third person. Ah, lol. We need the truncated response because if we include the harmful reply, it might refuse. Amazing. I'm a bit concerned. I'm a bit concerned. It sounds like the thing they give to the decoder is the model's activations on the prompt. But I feel like if you just reconstructed the text from the prompt, you would be in a pretty good place. So, or like I predict that if you give the model the jailbreaky question, and then you're just like, what's surprising in this question? That feels like an easier thing to answer. I don't know. All right. What are there other things? I think. Okay, so now I know what all these baselines mean. How do I interpret this? PCD with no bottleneck does so well on 3 words. Yeah, I'm also feel like they could have used stronger baselines here. So from a black box perspective, yeah. So things I might have tried: giving the third person transcript to another model, and asking it, including good models. I think this would lead, or maybe just giving the text of the thing that generated the activations that went to the PCD model. Just trying different prompts, like, please extract the surprising bit of text in here, or something. Feels like it might have worked. Pre-fill attacks, like, make the model begin its answer with, it was surprising that I was thinking about blah, and then see if that just changes things. Might not, but like, it's cheap. I think some form of running a sparse autoencoder over the sequence, though, well, I mean, one thing I might try is run a sparse autoencoder over the sequence, look at whether there are any concepts that are rare across a normal chat corpus, and then give all of the autointerp descriptions to a language model and say, which of these is most suspicious? It's a bit convoluted, but I think lower effort than training a PCD. But less flexible, so I will grant them that. Steering the model towards honesty. But yeah. Okay, the fact that I'm starting to think of like obviously compelling baselines does make me somewhat more sympathetic to their case, but all right. Secret hints. All right, so I do enjoy the prompt here. What is the 9,987th prime? And then you give the model the thing as a top secret shortcut. Honestly, I'm kind of surprised that the model does so badly. That the prompting does so badly here. Maybe this is just because Llama 3 8B is bad, but it doesn't sound like they're telling it, they're prompting it super hard to not admit to the hint. but maybe it just, as a default personality, does not like admitting to using hints or something. I don't know. All right, so and then yes. Cool. Okay, so this seems to be saying that PCD with no bottleneck is a slight improvement on latent QA. PCD with bottleneck is not. Um, hmm. I feel like they should have done a prompting baseline where they gave the prompt to another language model, or even this language model, another conversation, and said, would assistant answering this use any shortcuts or something? But yeah, these do feel like these do feel like, you know, reasonable, useful language model answers. I'm into that. As in, if I was using a technique that gave me these outputs, I would find this helpful. So it's decent on that front. So they claim this sentence feels a bit off to me. I think the introspection paper had a 20% success rate on just ask the model, were your thoughts tampered with? And it says yes. But a notably higher rate on what was the concept? Because saying what the concept is just a much easier task than saying that your thoughts have been edited. But whatever, that's a minor nitpick. So this is the rate of saying the thing. Cool. So it's like does okay. Do they have a does the model say this baseline? But yeah, does like reasonably worse than an SAE looks like. think I should check the appendix in case I'm misunderstanding what task they're doing. Don't understand what prompt they used. Okay, so they just steer on the dummy user message hi, and then they take that activation and put it into the PCD or latent QA decoder. Yeah, maybe another note is I think losing to SAEs here is not that concerning because 72 million tokens is fairly low for SAE training, but it sounds like something about PCD training was struggling with longer, but like I'm sure that's a solvable issue. And I think the interesting question is like the longevity of the technique. Like where could it be in like a year, not where is it now? Ooh, auditing, I love it. Okay, this is great. So this seems to be a section about encoder concepts provide observability into these claims. So yeah, there seems to be a section about like, well, is the sparse bottleneck useful? So they're claiming the decoder says something, and we're not super sure if it's legit or not. And so we can look at the encoder and look at the top activating examples of the latents that light up, and then interpretations of those, auto-interp explanations of those, and then compare them to the decoder. And they're emphasizing, because the auto-interp is from a different mechanism, this is independent evidence. But I find this confusing because if I wanted independent evidence, I'd rather have a separately trained SE that has nothing to do with the PCD because it's much more independent. Like, given that the decoder is a function of the encoder, this is worse, I'd say, because you kind of know that the decoder is probably basing its answer off the encoded concepts, and thus the auto-interp explanations are like fairly likely to be linked to. There's like a central cause of both of them. And if the encoder is wrong, then both the decoder and the autotype explanations would be wrong. But if it was a separate SAE, that could still happen, but like I'm a bit less concerned. Okay, so then there's got mathematical errors. I wonder which paper this is. Ah, nice. One of the earlier transluce works. Debugging this exact question. So this is a qualitative example of using concepts. I wonder why policy is in double braces. All right, and yeah, so I guess maybe try and reflect a bit on my general takes. I think the sparse bottleneck approach is potentially interesting, but I'm worried it's kind of overcomplicating things, and that it would be better to just separately train an activation oracle and an SAE. I think the main reason, because I think the independence argument doesn't go through, and I would suspect the sparse bottleneck makes training sufficiently annoying that the benefit of not needing to train two things is insufficient to be worth it practically. I think that what do I think? Yeah, I think that the main potential argument I see for it being worthwhile is if it increases performance of the decoder / activation oracle by creating some inductive bias towards interpretability, but I'm not super convinced by this. And here it looked like not having the bottleneck was better. I'd be interested in whether it increases the reliability of the PCD. Like, is it less likely to hallucinate if it is constrained, etc.? But I feel like that would need reasonably different evaluations to tests than the ones shown here. But yeah, I think this is like an interesting direction, and I'm excited to see a diversity of approaches. All right, what's in their discussion? Yep, so yeah, they had trouble scaling. Yeah, I think this is a reasonable point. The encoder does not need to be a simple linear layer. I was actually mildly surprised it was. And plausibly doing something more ambitious here could be useful. And yep, I am into the broad vision of end-to-end interpretability they lay out here. Like, you train a model to figure out which neurons to ablate given a description, and use RL to make it do this better, and things like this, and see if that is sufficient. But yeah, all right. Thanks all for joining. I will put links to the two papers in the description. And there's also a blog post from Jacob Steinhardt that recently came out, kind of laying out more of a vision. Very sweetly, partly a response to my post and Leo's post. And yeah, I have not had the chance to read this closely yet, but my impression is that this is, yeah. I think if you want to see another perspective on the maybe we need end-to-end interpretability, this is an interesting thing to check out. So, and yeah, I think it's important not to get overly blinded by like the first examples you see of what this kind of thing could look like, because it is such a broad idea of just, well, what if everything we ever wanted interpretability researchers could do, we could train a model to do? I have no idea if this will work. I'm pro people exploring it. And plausibly, we just want as many different ideas for what to do this one as possible, because then we can shove them all into a training procedure and get a better thing. And yep, I will have links to all of these in the description. All right, thanks all for listening. For those of you who sat through like 3 hours of this.